Good morning, everyone. Now, today I will introduce you to Sub-Riemannian geometry, an exotic field of geometry that has many applications in science and combines analysis and geometry. Now, today we will talk about Sub-Riemannian manifolds and their and some very useful techniques we have to study them. First of all, we will begin with some basic complex geometry, because this is very useful for our study. We will mostly define pseudo-Hermitian structures, and we will study them in the context of Sub-Riemannian manifolds. And then we will define Sub-Riemannian manifolds and give some examples. For example, we have the Heisenberg group, which is a non-trivial example, which is the simplest. And then we'll define the affinity group, which is a group we're studying. Next, we will introduce the Riemannian approximants. This is a technique that's very useful to study Sub-Riemannian manifolds. We can use techniques from Riemannian geometry to study things like the horizontal curvature, as we call it, and other invariants in Sub-Riemannian manifolds. And finally, we will introduce the Tanaka-Webster connection, which is a kind of a canonical connection for those types of manifolds. So let's begin. First, let's start with a manifold M of dimension 2n. Then this type of manifold is just we take it to so that it's homeomorphic, locally diffeomorphic to the complex plane. And we define a structure, an endomorphism on it, and we call it J, such that it satisfies J squared equals to minus I, where I is just the identity map. We call this structure an almost complex structure. And then we can define those types of bundles. We define T of 1, 0, M, like shown here, and T of 0.1 M, as shown here. Those two types of bundles, we call them the holomorphic and the anti-holomorphic type of bundle. And we can see this relation that they satisfy. So this is a decomposition of this thing, which is just the complexified tangent bundle. It's just the tangent bundle of this type of manifold, tensor product, the complex numbers. So essentially, it's the kind of an analog of the real tangent bundle, but for complex coefficients. And then this thing splits like this. So we can write this as a direct sum of the holomorphic and the anti-holomorphic tangent bundles. And we also have that the complex conjugation, which is, as we know it for complex analysis, induces an isomorphism of those tangent bundles. Here's a proof of this. Okay, so we know that the intersection of the holomorphic and anti-holomorphic tangent bundles is just a zero vector. We can see this easily from the very definition of those bundles. And we just define this canonical map, which we can prove is injective. To see this, we just compute the kernel of this map, and we see that's just a zero vector. And then we can just define the inverse map, which is this thing. And we see that a vector V just splits like those two vectors as a direct sum of those vectors. And essentially, this proves that this is an isomorphism. So we know that actually this decomposition that we mentioned actually holds. We can also check the second condition, which was this isomorphism. Just take the complex conjugate of this vector, and you see that it actually gives the required. So finally, we can define as Zi and Z bar I those two vector fields that we had from this decomposition. And Xi and Yi just elements of the tangent bundle. So those two vectors are just a different way to just write this orthonormal frame that we define eventually. So those are also useful. Now that we have, we can define we can take a map from the complex plane to the power of n, to the complex plane of the power n, and we call this map a holomorphic map if and only if this relation is satisfied. So we want the push forward of the map composed with J to commute essentially with J. So we want this. This is essentially the Cauchy-Riemann equation in the general setting of many complex variables. And we give a definition here. We will call a manifold dimension 2n a complex manifold if the charts are essentially the coordinates take us to the Cn plane space, and that the transition maps are essentially holomorphic. So when we change coordinates, this change should be holomorphic, and we call this a complex manifold. So a complex manifold naturally takes the complex structure from the complex plane and more generally Cn by using this kind of a relation. So just take the push forward of the inverse and compose it to J, and then with the push forward of these maps, the coordinate maps. Okay, now we introduce a twist. We will try to define a complex structure, but not on the entire tangent bundle, but only to a sub-bundle. So we'll define that a codimension S CR structure is just a manifold, a real manifold, with a 2p dimensional smooth sub-bundle of the tangent bundle. And we require some integrability conditions, like this vector we want it to belong to this 2p dimensional smooth sub-bundle. We call it H. And we want also this condition to be satisfied. And those are just the Lie brackets. And we can also, if we take S equal to 1, we can define a contact structure on this. And the contact structure is just essentially a one sub-bundle, so a codimension one sub-bundle. And we also have a one form such that this bundle is the kernel of this one form. And we call this form a contact form of M. And we require this integrability, this non-integrability condition. So essentially this means that this sub-bundle is non-integrable. And this comes from Frobenius theorem. And we also have another vector field T that satisfies theta of T equal to 1, and T belongs to the kernel of theta. And this theta and this T, just call it the Rib vector field. Okay, now we have, in a similar way, like the complex manifolds, we have this decomposition. So this complexified tangent bundle that splits into holomorphic, anti-holomorphic, and we have an extra term here, which is T is the Rib field. So we have this multiple of the Rib field. And we can define this sub-bundle, which is also the contact structure, as the real part of this thing. So we also need a way to measure how the holomorphic, the complex directions kind of twist with respect to the contact bundle. And this can be shown by the Levy form. which we can define as this. The Lebesgue form is just L theta of Z bar W, that's equal to minus I d theta Z bar W. And Z and W are just holomorphic vectors here. They belong to this bundle. In the XY frame, we also have the real Lebesgue form, as we call it. So it's defined like this. And we will see that this is actually a Riemannian product defined only on the contact distribution. We can also extend this Lebesgue form that we defined, this real Lebesgue form, into a metric, a Riemannian metric, that we call a Webster metric. So we can do this by just adding this theta squared. This is just theta tensor product theta. Just write it squared for simplicity, for compactness, say. And this satisfies some properties. So we have the first property is that j squared is minus 1 plus theta, the tensor product with t. And then we have that jt equals to 0. And theta composed with j is 0. And we have that g theta x of t equals to theta of x. And we have this final property. So we have this proposition here that when we have jx and jy inside this g theta, then essentially this gives this. And we can prove it easily. So we'll start. We just consider their difference, and using the definition of g theta, just write them like this. And then using the integrability condition we mentioned, we can write this as this. And we have the theta outside, and then we can, due to linearity, we have it here, and we use this relation to prove that it's actually 0. So essentially, this is equal to this. Okay, now we define Sub-Riemannian manifolds. Now, a Sub-Riemannian manifold is essentially a manifold that has that consists of a subbundle and with a Riemannian metric defined only on the subbundle. And we call this subbundle a horizontal distribution. Now, in our case, we essentially study manifolds such that the horizontal distribution is exactly the contact structure. So we want manifolds that actually carry a Sub-Riemannian metric and also a contact structure and a CR structure. And we can define the distance of points if we view this as a metric space, like as the infimum of all the curves that pass through 2 points. And those curves should be tangent to the horizontal distribution. So essentially, we have kind of like a, if we can draw this, we take 2 points and we draw all possible paths that are horizontal, which means that they are tangent to the horizontal distribution, and we take the infimum of all those curves. So essentially, this means that we're only allowing horizontal directions when we're considering distances. We can have, like in Riemannian geometry, any direction in the tangent bundle. We're only allowing this direction. So the first example is the Heisenberg group, which is defined as follows. It's just a Lie group, which is the product of the complex plane with R, and has this multiplication rule. So first, the first 2 elements we just add, and the second we add, and we add this 2 times the imaginary part of this thing. And so Ilia, who's also an organizer of this meeting, a seminar, created this nice animation of how the tangent bundle of the complex of the horizontal distribution of the Heisenberg group varies as we move along the points inside the manifold. So we can show you this animation.
Συγγνώμη, εγώ μπήκα για λίγο, θα βγω τώρα γιατί έχω δουλειά. Ευχαριστώ.
Okay. So you can see here, this is essentially the tangent at a specific point, and we see that as we move along points, how this varies. In this particular case, we consider the tangent bundle that is tangent to a point A, B, C, and this is as A varies, we see how this twists. You can also see and have another example and see how it twists when B varies. So we can see this. So when B varies, essentially the tangent bundle kind of twists like this. And when C varies, it kind of moves like this. So thanks, Ilya, for creating this animation. Now, so we can see that the Heisenberg group has this left invariant orthonormal frame that we define as follows. T is just the Rib field here, and X and Y just span this horizontal distribution. We define a contact form given by dt plus 2x dy minus 2y dx. And we have also a CR structure that is defined as jx equal to y and jy equals to minus x. We also have the non-vanishing lip brackets, which are x and y equals to minus 4t. And this may be familiar to people working in quantum mechanics, as this actually gives the commutators between position and momentum. This is kind of very familiar to this thing. So you can actually prove the Heisenberg inequality, the Heisenberg uncertainty principle, by using this Robinson-Schrödinger inequality from this thing. And this gives us the application of the Heisenberg group. We see that the Heisenberg group, as the name suggests, by the famous physicist Werner Heisenberg, has applications in quantum mechanics. You can also generalize the Heisenberg group to the n dimensions, or actually 2n plus 1 dimensions. And we use this product here, which is very similar to the product we use in the n equals to 1. And we define it as Cn times R. And the left invariant orthonormal frame is very similar. Now, this is orthonormal with respect to the Webster metric. If we only consider the Levy form, which is the Sub-Riemannian kind of metric, then this is orthonormal. Another useful example is something that we are studying is the affine additive group. And this is defined as follows. We have the real numbers times the positive real line times the Heisenberg group, which is the nth minus 1 Heisenberg group. And this is this has this kind of a weird product. First we sum, and then we multiply, and then we have this weird product here. We can also see that the inverse of this Lie group is this. And what's very interesting about this is that when n equals to 1, and this is just the hyperbolic plane. So in this case, we just have R times the hyperbolic plane, which is one of Thurston's 8 geometries. And the finite additive group has this orthonormal frame, and this is the Rib field here. And here are the non-vanishing Lie brackets. We also define a contact form, an AA, given like this. And we have a CR structure defined as this. Okay, now we will study a very useful technique to study Sub-Riemannian manifolds. This is called the Riemannian approximant method. The idea is that we take the Sub-Riemannian metric, which is defined only on the horizontal distribution, and we extend it into a family of metrics which are Riemannian, and then we can study those metrics and use techniques from Riemannian geometry, and then just take the limit and go back to the Sub-Riemannian. So here's how we do this. We can first define theta epsilon as epsilon times theta. This is just the contact form. And the Riemann field, we define it as T epsilon is equals to T over epsilon. The reason we define it like this is so we can have this relation to be satisfied. So we want theta epsilon acting on T epsilon to be equal to 1. And then we can define a one-parameter family of metrics as follows. So it's G epsilon equals to GCC. GCC is the Sub-Riemannian metric. Now, what does CC stand for? This means essentially Carnot-Carathodori. This is usually we write it like this. So we have this Carnot-Carathodori type of metric, and we add epsilon theta squared. So this is very similar to the Webster metric. The only difference is that here we have the epsilon, and for epsilon equal to 1, just return to the Webster metric. If epsilon is 0 and we neglect this term, then we're just going back to the Sub-Riemannian metric. So we can also extend this structure such that J of t equals to 0. And this gives us an orthonormal frame, which we have here is x1 to xn, y1 which is just the jx1. So the way we define it is like this. And then we have T epsilon, which is our Riemann field now. Okay, now we want to see the convergence of metrics. So we want to kind of formalize this idea of how those metrics converge. And first, we need to study this space of spaces type of thing. So we try to embed metric spaces inside another metric space and try to compare those to see how one can somehow converge to the other. We try to formalize this idea here by a kind of a concept called the Gromov-Hausdorff convergence. So we can first define the Hausdorff distance, which is just the infimum of all epsilon, such as epsilon1 is a subset of this epsilon neighborhood of epsilon2, and epsilon2 is a subset of the epsilon neighborhood of epsilon1. The epsilon neighborhood is just what one can imagine is just all the points that are of distance less than epsilon than this epsilon I. So this is the epsilon neighborhood, and we want this kind of way to compare those subsets of a metric space. So we can give a definition here. We can define the Gromov-Hausdorff distance as the infimum of all the Hausdorff distance between f of x and g of y, where f is just an embedding of x into some metric space, and g an embedding of y into some metric space, and we take the infimum over all f, g, and z is just the metric space we're trying to embed x and y. And then we say that a sequence of compact metric spaces Gromov-Hausdorff converges to a metric space X if this distance, the Gromov-Hausdorff distance, goes to 0 as n goes to infinity. Okay, now we have a sequence of proper pointing length spaces. I will explain what this means. So proper means that all subsets, all closed balls are actually compact. Pointed means that we have some kind of a base point in its metric space. And length means that any two points can be connected by curves, or to put it better, you can find the distance between 2 points as the infimum of all curves that have finite length and pass through those 2 points. So you consider those types of metric spaces or length spaces, as we call them here. And we say that those converge to the length space xdx if the sequence of those closed balls, Gromov-Hausdorff converges to this ball here. And we want this convergence to be uniform in R. So essentially, we give kind of a different way to study this convergence. Instead of studying the convergence of the metric space themselves, and we study the convergence of balls. So here we have the proposition we need to prove. So we want to see essentially how those Riemannian approximates converge to this Sub-Riemannian kind of metric. And we start with a set. X is a set equipped with a family of metrics, dt. And we have a K compact set in X, and we define omega K as this. Then we need those 3 axioms here. For example, the first, we have that for T greater than or equal to 0, then we demand that this is a proper length space. Then we also have that the function T to dt of x and y is just non-increasing. And for each compact set K in X, we have that omega K of epsilon goes to 0 as epsilon goes to 0. And then we claim that those metric spaces converge in the sense of Gromov-Hausdorff to a metric space X d0. And let's prove this. Okay, so for a compact set K, you see that this map is increasing. Now you can easily see this from the definition of omega K. And we can also see that omega K is sublinear. And you can prove this inclusion here. It's a double inclusion. Okay, so using this, so specifically we want to use the fact that omega K is increasing, and this property here is 6 property, the inclusion of balls. Actually is non-increasing. And we use this to prove this identity here. So this inequality that dt of xy is less than or equal to omega k of t. Now you can see this from this inclusion here, and using the fact that we have here, it's non-increasing t of t to dt, you can easily see that we can get this inequality. Then we just fix a base point, x0, and we want just to prove that the compact metric balls converge to be 0. And we do this for each radius greater than 0. So we should restrict ourselves to the case where we have the ambient metric space, that we call it Z, and we define it as K times this interval 0, 1. And we use this metric here. Now, as an exercise, one can prove that this is actually a metric. So I won't do it here, but it's a nice exercise. So you can see that this map is an isometric bending, and all we need to do now is just prove that the Hausdorff distance between the balls that tends to 0 as t goes to 0. So we claim this thing, and once we have this, by the assumption 3 we have, which is this assumption, we can easily see that we get the required. So to see this, we just take a point in B0 and another point in BT, and we have this, that the distance between xt and x0 is equal to omega kt plus t, and this is bounded by 2 omega kt plus t. And essentially, we use 7, which is essentially this thing that we prove. Using this, we can essentially find this bound here, which is exactly what we wanted. And using the assumption 3, you can just get the required. So essentially, what we have proved is that this family of metric spaces actually converges to the Sub-Riemannian metric. Okay, so one final thing I'd like to mention is the Tanaka-Webster connection. So we want a canonical connection on those Sub-Riemannian manifolds. Essentially, we want something that can that is very compatible with a CR structure, and of course with a Levy form. And the Levi-Civita connection is not the one to use here. So we need something else. And this is essentially the Tanaka-Webster connection. And we define it as follows. So it's a unique linear connection. Now this is a theorem, but you can see how this is defined. So we claim that there's a unique linear connection, nabla TW, that satisfies the following. First of all, that this H of G is parallel with respect to this nabla. This means that essentially the covariant derivative of any section of H just belongs to H, to a section of H. And we have here this compatibility condition with the metric. This is the Carnot-Carathodori metric. And the compatibility condition with the CR structure. Now, the thing about this Tanaka-Webster connection is that it's not torsion-free, like the Levi-Civita connection. So here we have torsion. And in Sub-Riemannian geometry, the torsion is always non-zero. If it's 0, then we have another type of manifold. We call it a Sasakian manifold, which is Riemannian. So we want the torsion to satisfy this relation here and this. And we have that the torsion composed with J can have anti-commutes with J. And so we have this anti-commutativity relation. So I will give a sketch of this proof. This is a very long proof, but just to get the idea of how this is proved. First, some preliminaries. So we want to define this projection here. This is P plus. It's just a projection of the complexified tangent to the holomorphic bundle. And P minus is just the projection to the anti-holomorphic bundle. And we observe that this thing is true. Now we can see this from the definition of the holomorphic and anti-holomorphic bundles, and of course P plus minus. And just define omega to be minus d theta. And we defined kt to be this minus over 1 over 2, j composed with, this is the Lie derivative with respect to t of this CR structure. So first, let's prove that this connection actually exists. So we define this kind of map here. We don't know it's a connection yet. So we define it as this map between the sections, this product of sections of the complexified tangent bundle to these sections of the complexified tangent bundle. And we define it as follows. So we want all of this to be satisfied. And with this x and y belonging to the holomorphic tangent bundle. U here is defined as follows. So we define it using this omega, although we define it equals to minus d theta, and satisfies this. Now, one can check that this is actually a linear connection. So essentially all those properties here suggest that it satisfies all the conditions to be a linear connection. So this is enough at this point. Now, we want essentially to see that this linear connection actually satisfies all the axioms that we mentioned in the theorem. Now, first, let's observe that the Lie derivative of theta with respect to t is just 0. And using this and this relation, which is a property that we mentioned of the Webster metric, that j squared equals to minus I plus theta tensor product t, then we obtain this relation. You can also see that the Lie derivative of sections of H belongs to the sections of H. Now, by the above and the definition of KT, we obtain this relation. And again, we can just use this relation of the omega that we actually proved to get this, that the Lie derivative with respect to t plus kt of those sections of the holomorphic bundle, this belongs to the sections of holomorphic bundle. We can see that the derivative of omega is just 0. And we notice that this essentially expression holds. So we can show eventually that omega of ktx, y plus omega x kty is actually 0. And then essentially using all this, so using this relation, this, and this, we can check essentially the axioms and see that they're actually satisfied. Now, the computations that are behind this are non-trivial, but I just had to omit them to save time. Now, let's prove uniqueness. So essentially, we start with two holomorphic vectors, vector fields. And by two, which is, let me remind you what is this. It's this thing here. By using this relation, we can eventually obtain this formula here about the Lie brackets. Now we can see that this covariant derivative of z with respect to y bar and the covariant derivative of y bar with respect to z belong to the holomorphic, to the sections of the holomorphic and anti-holomorphic tangent bundles respectively. So eventually we get this identity. And since we have this relation here, this is due to the contact structure, the way it is defined. So we see that this nabla of the metric, of the Carnot-Carathéodory metric, can be written as this. So now we can take essentially we have two cases. The first case is that y is equal to t. So y is equal to the Rib field. In this case, we get this. And no, this is another, this is a case when z equals to the horizontal bundle. And using this previous relation, we get that this is equal to 0. And if z equals to t, then we get this. So since the covariant derivative of omega is equal to 0 and the previous relation, we can obtain this thing. after the computations, and by this thing, you can obtain this. So eventually, this, and this thing here and this thing give us uniqueness. So the idea was to just kind of eliminate all the degrees of freedom. So think of it, if we were to do this on coordinates, we have to write the covariant derivative or the connection in terms of the Christoffel symbols. So what we did actually here is we essentially computed all the Christoffel symbols, but in a kind of a coordinate independent way. So we kind of removed all possibilities. So essentially this gives us uniqueness. And that's it. Thank you for your time.
Πολύ ωραία, Δημήτρη. Μπράβο. Έχει πολύ ενδιαφέρον αυτό το πράγμα, γιατί αν πας λίγο τις διαφάνειες πίσω, ας πούμε, μια σχέση που έχεις τώρα στο τέλος, πήγαινε λίγο τις διαφάνειες.